Good afternoon, everyone. I think we've crossed over to afternoon by this point. I am Julia, and I'm here with my team today. This is Judy, Sunny, Monik, and Gordon. And we are here to tell you about what we did this year, which was working on an innovative actuator for aerospace applications for TE Connectivity. TE Connectivity is a company that designs and manufactures connector and sensor products for a variety of industries. Specifically, one of their primary clients is the aerospace industry, for which they provide actuators and relays. Relays are used for a variety of applications in airplanes, one of them being deploying landing gear. So let's give you a little bit of a background. What is a relay? A relay is an electrically activated switch used to transfer current. And an actuator is the mechanism inside the relay that performs the switching. So you can think of it just as like a standard light switch. However, instead of using your hand, the actuator does that motion for you. So when the relay is off, just like a light switch, nothing happens, no current is provided through, and your light bulb or other part isn't working. However, what the actuator does is when the actuator itself turns on, it pulls that switch to the closed position, turning the relay on, allowing power to get through to whatever component you need to have on. So relays are used in airplanes, as I mentioned earlier, and there can be any number from kind of 0 to 100 relays in any given airplane, and they do a lot of different jobs. They do things such as I mentioned earlier, landing gear. That's a one-time application for a flight, right? So you get ready to land, and your relay gets you going for getting ready to land. Next is something that happens a lot more intermittently, cabin lighting and AC. The relay does this on its own, so throughout the flight, it lets out enough cool air to allow the temperature to stay at usually at a comfortable place. Next is propulsion. This is also one that happens a lot throughout the plane. You got to keep that plane going, and the relay does that for you, so it allows the gas to go through into the engine. So what is the challenge? Currently, relays work great. They're used in a ton of applications. They're super reliable. However, they're very heavy. As you might know, plane tickets are already very expensive, and aerospace companies do as much as they can to lower the weight and to lower the cost of fuel. So currently, they use these large coils, copper coils, which allow them to be small but heavy. So our task was to create an innovative actuator that performs all of the same functions, but reduces on weight and uses some kind of novel concept. So getting into our process a little bit, since we had to start with a novel concept, we were starting from the beginning. Well, what's out there? What are we looking into? So we were ideating, we were researching, we were performing a bunch of concept tests to really get a sense of what kind of applications are out there, what can we look into. Then we narrowed and refined, and we spent a lot of time fabricating, creating more tests, validating, and creating a detailed design, because what we ended up with was a prototype that we could hand to TE that does function. So getting into that beginning of the process, as I said, we went through a lot of ideas. We looked at things that were purely mechanical. We looked into pneumatics, magnets, carbon nanotubes, electroactive polymers. If you don't recognize these things, that's okay. And then we looked into them specifically for weight, reliability, speed, and travel. These are the key requirements that TE needs to be able to have a relay that is reliable in an airplane. So then we narrowed down based on these key factors, and we got to our best results. Our best result was shape memory alloy. Shape memory alloy is a unique metal. It has this property where it has an original remembered shape. For our purposes, we're going to say it's a straight line. You can then deform that shape with a force. So we're going to put it into this nice right angle here. And then once this shape is deformed, you can reheat it. When you apply heat, the shape memory alloy returns to its remembered shape, returning to a straight line. So we exploited this application of shape memory alloy, and we specifically used coils. So we had our remembered shape be a small compressed coil or in a spring format. And then when it relaxed, when the heat is removed, it goes back to an expanded spring. Once we had the shape memory alloy, we had to test it and make sure that it had all of these key requirements that TE was requiring of us. So first thing we did was the force. So what's the maximum force that an SMA can overcome? Airplanes are harsh environments sometimes, and so it needs to be able to get through that. Also the life cycle and decay. How many times will the SMA move before it dies? As I said, for certain things like propulsion, it's important that it can keep going for a while. And you don't want to be changing this after every single flight. Next is the travel. How far can the SMA move? This is important because for larger applications, relays need to move further to be able to get through and transfer that larger current. And next is the speed. How fast can the SMA move? Again, with things like the landing gear happens once, or the lighting, not that important if it's a half-second delay. However, if that's going in through your propulsion, you need to get gas to the engine as quickly as possible, so making sure that it can perform all of these critical applications. So we were actually able to create our final design. Here's a diagram of what a prototype looks like. And we're going to start talking about this from the outside in. So the entire thing is an isolated chamber with oil bath to allow increased temperatures. Essentially, as I said, the SMA is heated. When we want it to relax so that it can turn off, it's easier to do that in oil because it dissipates heat more quickly. Next, we have here the spring SMA actuation mechanism. There are two on the right just to allow for some increased force. And when the electrical current is passed through this contact on the right, the SMA actuates, going to that remembered position, moving it over to touch those contacts. So now the relay is turned on. We, on the other side as well, as you can see, we have two other SMAs. We decided to do this to have kind of as a counter SMA, what we call. So even though the oil dissipates that heat, causing it to relax, it doesn't do so extremely quickly. So those counter SMAs are just to give it that extra nudge and pull it over to the other side to be able to turn it off quickly. So when that does that, it goes back to the middle, and now the relay is turned off. So our accomplishments of this project, we were able to reduce the weight by 80%, which is a pretty great weight reduction. This was compared to a current relay that travels the same distance that ours does. As well, it was able to achieve 35,000 life cycles. We were able to actuate an 8mm distance, which is on the higher end of the actuation spectrum. And we were able to get it to actuate every 0.5 seconds. We also have a patent pending, which we are very excited about, and just filed that application. Lastly, we'd like to thank everyone at TE. This was a great project to work on, a lot of exciting things, as well as Alexandra Costa-Strong. She was our faculty advisor, helped us out a lot. Marcus Priest, our TE Connectivity Liaison, as well as Carl Kitts and Dan Hansen from TE Connectivity, who helped us out along the way. Thank you.